All right, so that might look something like this. We have our resistance RC. Because this is a common base amplifier, we are taking our output at the collector terminal. We are going to be applying our input at the emitter terminal, but we will have some signal resistance here, like so. And we're now going to mess things up further by including some base resistance R sub B. Okay. So this is both similar in some ways and dissimilar to what we've done previously. And so we're going to look at some of those similarities and dissimilarities to figure out how to determine the input resistance, output resistance, etc. Okay. So obviously, the input resistance that we're looking for is what we see looking into the input term, right? Now, I'm going to call this quantity Rn prime, which is looking directly through the emitter terminal. Okay, so do we have a configuration that we've seen before that looks something like this? So one that we analyzed previously was the effect of having an emitter degeneration resistor and a base resistance, right? Well, we don't have an emitter degeneration resistor here, but if we look at our notes for emitter degeneration with base resistance and just set RE equals to infinity, that's exactly what we have when we're looking in through the emitter terminal, right? So we're saying that our emitter resistance is an open circuit. So Rn prime is simply, so let me get my notes here. One over RE plus 1 plus beta divided by R pi plus beta all to the -1 power. So effectively, it's our emitter resistance in parallel with the reciprocal of this guy. Well, if this is an open circuit, that bit just goes away. From this, Rn with no prime is simply R sig plus R pi plus beta. Oh, did I write that correctly? Excuse me, that shouldn't be beta, that should be RB. My apologies. I'll fix that in the thing above. Times beta plus 1. Very sorry about the mistake here. Where I'm using the reciprocal here because I have this to the -1 power. So that's our input resistance with really not a whole heck of a lot of work based on our previous analysis. All right. Our output resistance is determined looking in to the output tank. Based on our prior analyses, what do you think this is going to be? RC. Over and over and over. All right. So the last last thing that we need to determine then is our voltage gain. So to simplify the determination of the voltage gain, let's call this nodal voltage here VE, or the emitter voltage. And so what we're going to try to figure out is some relationship for VE over VN, multiply that by some relationship for V out over VE, and this will be our voltage gain, V out over VN. That's what we've been doing. So let's start with that second part, V out over VE, because that could be familiar. If we're considering this circuit minus that signal resistance R sig to be a common base amplifier with a base resistance and emitter degeneration, where RE is effectively infinity, go back through your notes and see if the gain, when an emitter degeneration resistor and a base resistor is in there, actually messes anything up. Does it? So this term right here, V out over VE, looks like beta RC over R pi plus RB from our previous notes. Okay. How are we going to figure out VE over VN? Anybody have any thoughts? As a voltage divider, it's pretty much always a voltage divider. It's either a voltage divider or I'm trying to trick you and all of the signal gets passed through. Those are pretty much the only two options. Legitimate. Okay? So the voltage division is going to occur. This is going to be our new denominator for our voltage division relationship, our transfer function relationship. And the numerator is just going to be this part, because we're looking for the voltage drop from this node with respect to ground over R sig in series with this guy over here. So that means this relationship is R pi plus RB divided by beta plus 1 all over R sig plus R pi plus RB all over beta plus 1. Okay. Now, to make things simplify a little bit, what I'm going to do is I'm going to multiply R sig by beta plus 1 over beta plus 1 to give me a common denominator of beta plus 1 in both my numerator fraction and my denominator fraction. Right? So what I'm saying is that we could write this as R pi plus RB over beta plus 1 divided by R pi plus RB plus R sig times beta plus 1. All of that is divided by beta plus 1. Everybody okay with my algebra here? So effectively just multiplying this guy by beta plus 1 over beta plus 1. A weird way to express the number 1. Done. Right? Effectively, I'm doing the exact same thing. Yeah, I'm treating it as a slightly different way. I'm just multiplying this guy by beta plus 1 over beta plus 1, and then I can see that I can cancel those guys out, which gives me the exact same result as what you suggested. I didn't think of doing it that particular way. So 6 to 1, half dozen of the other. The result here, this guy cancels this guy, and I'm left with R pi plus RB divided by R pi plus RB plus R sig times beta plus 1. So finally, if I multiply this by this, I have an R pi plus beta in the numerator and an R pi plus beta in the denominator. They cancel each other out, leaving me with beta RC over R pi plus RB plus R sig times beta plus 1. So we didn't have to do literally any new circuit analysis whatsoever to figure out what was going on. It was all based on our previous. So the last configuration that I want to look at is our fully biased common base amplifier. So that's going to look something like this. Here's our resistor RC. We're going to take our output voltage here. We're going to have an emitter resistance here. Call this C coupling 1. Here is our signal resistance. Here's where our input voltage is applied. Then on the right-hand side, we are going to have a resistor R1, a resistor R2, and then some base capacitance. And up here is our power supply voltage, VCC. So let's talk about what this guy actually looks like at the small signal, right? So for small signal analysis, we treat our capacitors like open circuits and short circuits. Short circuits, okay? So our capacitor CC1 and its capacitor CB are both short circuits. VCC, our power supply voltage, is now an AC ground. So what does this capacitor CB actually do here? Why is it included? It shorts the base to ground, but it also shorts out resistor R2 and resistor R1, so that we don't have any base resistance actually applied at all. Okay. From our previous examples, we saw that the presence of base resistance tended to actually lower our voltage. We'll do an example probably in a minute that shows that. Okay. So a simplified version of this circuit looks something like this. So we have RC grounded on one end. Here's our output voltage. Here's RE. Here's R sig. Here's VN. Down this guy. So this should look fairly familiar. All right. So at least parts of it, that's kind of the whole point of this thing. So let's talk about our input impedance. Obviously, what we're looking for is this part, right? But from our past experience, we know what we see just looking up from the emitter terminal, right? What was that? One over GM, absolutely right. What do we see looking down from the emitter terminal? Not a trick question. RE. So from that, our input resistance, Rn, is just R sig plus 1 over GM in parallel with RE. Anybody not okay with that? What do we see for R out? Same thing we've seen every time we've looked at. Yeah, it's R sig. All right. For our voltage gain, we're going to do the exact same thing we've been doing. We're going to break it up into 2 stages. So I'm going to call this node VE. And I need to figure out, so I'm going to say that my voltage gain AV is VE over VN times V out over VE, right? So what's V out over VE? What does this look like if this signal resistance was shorted out? Right, but I mean, what does the circuit look like? Right? If this signal resistance right here were a short circuit, this amplifier would be a common base with emitter degeneration, nothing else remotely fancy, right? So what is V out over VE then? VMRC. All right. Let's talk about this guy here. What do we have at the actual input? Another voltage divider. Always a voltage divider, or all of the signal gets passed through. Okay? So what should our ratio be here? How did we do it literally the last example? We looked at our input resistance, and it's the part of the input resistance that the drop occurs over divided by the input resistance, right? So it's just going to be this guy divided by this guy. All right. So when we multiply those two quantities together, well, it actually doesn't look like I simplified it any further than that. So I'm just going to call it GMRC times R sig plus RE in parallel with GM to the -1 power. And then RE in parallel with GM to the -1 power here. And I have a stinging suspicion that if I had bothered to go through and do a little bit of algebra, this GM and these GMs would wind up canceling each other out in some odd looking way. But that's pretty simplified, so let's leave it like that. So this is the last common base amplifier circuit. We've effectively covered any and every possible permutation of how I can mess with things to make your life more difficult. But generally speaking, this is what the circuit, the practical application of a common base amplifier will look like. Okay. So, numerical example problem time. Let's say that I have the following circuit. And you are given the following pieces of information. IC is equal to 3.5 milliamps. Beta equal to 100. And VA is equal to 10 volts. Okay. So on an exam where time is of the essence, I will probably set your problem up like this, where I effectively tell you what the DC bias point parameters are, so that you can jump straight into figuring out what your small signal parameters are, right? So I'm not gonna, on your exam, I'm not gonna make you calculate IC and VE again and all that kind of stuff. That was the purpose of exam 2. Now, under the assumption that you know how to make those calculations, let's work on our small signal representation, right? So I have 3 small signal parameters that I have to care about. GM, my transconductance, R pi, the dynamic resistance of the diode portion of my BJT, and R naught, which is the resistance given by my early effect, if present. What's that? 300. Let me write that larger. Oops. $300. So 150 ohms for our collector resistance, 300 ohms for our emitter resistance, 7 kilo ohms for our resistor R1, and 11 kilo ohms for our resistor R2. Okay. So what do you guys think the first step in analyzing a circuit like this is? identify what type of amplifier, even broadly speaking, it is, right? So our input signal is being applied at the base. Our output is being taken at the collector. So what does that mean? Common emitter. Absolutely right. Anytime we have the input applied at the base and the output taken at the collector, we have a common emitter signal. Effectively, whichever one doesn't have the input or the output it's common that one. Okay. So we have a common emitter signal. All right. How can we simplify this model? Okay. So the simplification always involves turning our DC voltage sources off, so setting our power supply to AC ground, and shorting out all of our capacitors. So if we short circuit our capacitors and set VCC to be ground, what this looks like is a collector resistance. We're taking our output at the collector terminal. This capacitance CE effectively shorts out our 300 ohm resistor. So this guy right here looks like ground. Just going to scroll up here real quick. So connected to the base, we have a 7 kilo ohm resistor between the base node and ground, and 11 kilo ohm resistor between the base node and ground, which means this 7 and this 11 up here in parallel. I'm just going to call that R1 in parallel with R2 for right now. And here is our input. So what does this look like? Is this one of the fancy permutations of our common emitter amplifier, or is it more one of the simple ones? We don't have any emitter degeneration, right? We have a resistance tied to our base, but we don't have a voltage divider circuit for this one, right? Because obviously, since this is all of one node, all of our input signal gets passed to literally the base terminal, okay? So I would argue that this is just our simple common emitter amplifier with the early effect included because we were given a value for VA. All right. So let me put a dashed line here. Just to be clear. Everything to the right of this line looks like a common emitter core with early effect. So earlier I mentioned something about determining the small signal parameters, and then I got distracted, and then we went off and talked about other things. So let's circle back around to calculating those small signal parameters. There are 3 for any BJT amplifier that we're going to deal with, right? Our transconductance GM, our resistance R pi, and our resistance R naught. So how do we calculate GM? Presumably you guys have been taking notes, look it up. IC over VT, absolutely right. So if we plug in our value of IC that was given to us, 3.5 milliamps, and our thermal voltage of 26 millivolts, we get a transconductance of 134.615 millisiemens. Okay. By all means, you got a moment to type crap into your calculator and verify that I'm not blowing smoke up your butt. Do so. Our next small signal parameter is the quantity R pi. What's that going to be? Theta over GA. Which in this case would be a value of 742.857 ohms. And then lastly, we have our quantity R naught. How do we determine that? dA over IC, absolutely right. And this number comes out to be 2.857 kilos. Typically speaking, R naught will be larger than R pi. It'll also typically be larger than RC as well. Okay. Not to put the cart too far ahead of the horse, but one of the things that we're going to be doing next quarter is looking at these amplifier circuits with what are called active loads. Okay. So all an active load is we're replacing some of these resistors with transistors. And the reason that we're going to do that is because at DC, we see a pretty large resistance here, 150 ohms, right? Which is going to cause a large voltage drop, depending on how much current is flowing through it. Well, for these transistors at DC, they represent very small voltage drops, but at AC, they look like pretty dang large resistors. So that's going to that's literally how in modern analog electronics, like the processors in your computers and all that kind of good stuff, what do you think the supply voltages that they actually run at are? At this point, less than a volt. Less than 1 volt. Okay. So the only way to make that work is to not use physical resistors literally anywhere. All of the resistances are active load transistors. Okay. We'll talk about that much more in depth in a little, or in 336. But anyway. So we have our small signal parameters. We know very well, or at least we have notes on how everything to the right of this dashed line behaves, right? So our only real question here is what effect does this parallel resistance of R1 and R2 placed between the input node and ground have on how we know this circuit is supposed to behave? Let's talk about our input resistance, right? I'm going to ask you guys for input resistance, output resistance, and voltage gain. Okay. So for our general, actually I drew that poorly. Common emitter amplifier. To determine the input resistance, we would just look into the base terminal, right? What would we see? R pi. With the early effect included or not? Does the early effect change the input resistance? All right, there's just R pi. So if Rn prime is just R pi, what do we see looking in here? We're still looking in through the input terminal, right? So we should see between this node and ground, R1 in parallel with R2 And then between this node and ground, we see R pi, right? So our input resistance should literally just be R1 in parallel with R2 in parallel with R pi. Plug these numbers into our calculator. We see that we get an input resistance of 632.943 ohms. Output resistance is this quantity, right? So what do we see looking into the output terminal? RC in parallel with R0, absolutely right. This extra resistor here doesn't do anything. $124.8 ohms. So we could call this node right here VB and figure out what V out over VB is, and then figure out a relationship for VB over VN. But it should be pretty obvious that VN is our base voltage, right? So for a common emitter amplifier with early effect included, what should our voltage gain be? Exactly right. Negative GM times the parallel combination of RC and R0. Which comes out to be negative 16.8. And I always give my voltage gain units of volts per volt, but you don't have to if you don't.
What is the R1 and R2 parallel non-effect gain?
Okay. What is the transfer? Let me draw this in a different way. So I have at my input stage this circuit where I just have some arbitrary resistance R. What's the transfer function of my circuit? What's the input output relationship? Which is why that resistor doesn't mess with it, right? Yeah, if instead I had a resistor in series right here, that would absolutely change that relationship. But because this resistance is in parallel with our input voltage signal, it doesn't make any change to it. How did this feel as a numerical example? All of these problems, all this kind of good stuff is going to be a whole heck of a lot of, wait, what does this look like again? Let me go find it. Then I use this equation, which is why I'm not going to be an ass and make you memorize all of them. That'd be terrifying, right? All right, let's look at another example. in C1. Let's say that this 3.3 volts up here. Let's say that this circuit is biased such that the collector current is 400 microamps. Beta is 100, and our early voltage is infinity. What kind of circuit is this? Just without too much detail, which of our three different types of amplifier does it have to be? So there is some form of emitter degeneration for sure, because there's a resistor placed between the emitter terminal and ground. But is this a common base, a common collector, or a common emitter amplifier? Common base, right? Anytime the input is taken, or excuse me, the input is applied at the emitter terminal and the output is taken at the collector terminal, it is a common base amplifier. As Mr. Boyle suggested, this is a common base amplifier with emitter degeneration, right? Do we have any base resistance or anything like that? We do not, because this capacitor here, CB, looks like a small signal short circuit, which shorts out the 22 kilo ohm resistor and shorts out the 50 kilo ohm resistor. Okay, so we're going to work this problem once. He is shorting things out, and then we're going to work it again where CB isn't shorting things out, and see what the difference in the gain is and why we do this. All right. So what are my small signal parameters? How do I calculate GM again? IC over VT. I get that to be 15.385 millisiemens. R pi, how do I determine that? Beta over GM, absolutely right. Which I get to be 6.5 kilo ohms. And then in this case, since VA is equal to infinity, R naught would also be infinity. All right, so let's draw the simplified version of the circuit. I like to do that. Okay. So our simplified version again comes from shorting out all of our capacitors, setting all of our DC voltages to 0, which means that we ground our power supply voltages. And so what we're left with is just this guy. So, as was suggested previously, this is simply a common base amplifier with emitter degeneration. So, what should my input resistance be? This is literally directly out of your notes. We shouldn't have to really think about anything, right?
1 over D and then parallel RE.
exactly right. 1 over GM in parallel with R8. Which looks like 45.349 ohms. So I know we have different values for things, but we can see here our input resistance for this configuration is pretty small. What's our output resistance going to be? Yeah, just RC, 500 ohms. And finally, our voltage gain, GMRC. Which is going to look like 7.692 volts per volt in this case. Okay. All right, so let's revisit this if CB isn't there. I don't mean we're shorting it out, I mean we're open circuit. Okay. If we're shorting it out, it wouldn't make any difference whatsoever. What change would we see on our simplified model? So we'll have R1 and R2 in parallel because they're no longer shorted out. Where are they going to show up? Right, so they're going to be between the base and ground. So effectively, that would be like putting a resistor here. That is R1 in parallel with R2, right? So, if I am not mistaken, for our equations for common emitter, or excuse me, common base with a base resistance and emitter degeneration, they make reference to a base resistance RB, or obviously RB in this case is just R1 in parallel with R2. Which will be 15.278 kilo ohms. All right. What's our input resistance in the case of a common base amplifier with both base resistance and emitter degeneration? Yeah. All right. So when I plug those numbers into my calculator, I get 150.653 ohms. So the inclusion of a base resistance here made our input resistance increase by roughly a factor of 3. All right. What's R out? Still just RC, yeah, so 500 ohms. And then lastly, our voltage gain. So what's our voltage gain for this particular configuration? Beta RC R pi plus RB, which I get to be 2.296 volts per volt. So the inclusion of this base resistance caused our input resistance to increase by a factor of roughly 3, but it also caused our voltage gain to go down by a factor of roughly 3. in 336, when we start talking about these circuits as feedback amplifiers, we'll find out exactly why one goes up while one goes down. All right, so numerical examples, hopefully not particularly difficult. All I can ask you to do on your exams, homework, etc., is stuff literally just like this. Yeah, I was going to say last year I gave the students a bonus assignment worth a couple of points. That was, I think it was a BJT amplifier like this, except that it did have active loads instead of the resistors. I may give that to you guys as well if you feel that you are in need of some sort of bonus points or something like that. Anyway. All right, so that's enough out of me for today. So we're knocking off 20 minutes early. Enjoy. Donald, what's up?
What's the point of having there if it's gonna short circuit everything as opposed to just ripping out all the stuff that short circuits? Just putting in short circuit?
Okay, so that's actually a pretty good question. All right. Why do we use a capacitor here? So the capacitors are used because at DC, they look like open circuits, okay? Which means that we have a full bias network that's setting a very stable DC operating point for the circuit. We use these capacitors to make the parts of the DC circuit that lower the performance of our system go away at a small signal or AC level, right? So if we didn't have this 50 kilo ohm resistor and this 22 kilo ohm resistor here establishing our bias point, that means that we would have to come up with an external voltage source to give us whatever voltage that we need to bias this guy correctly, right? If we only have access to a 3.3 volt source, the correct way to bias this is to choose the resistors such that we get a bias voltage of whatever we need to drive our particular amount of current for our amplifier, right? If we don't have these resistors, we have to replace this resistor network with literally some form of battery or something like that, which doesn't make any sense. So the capacitor here keeps the DC bias point stable while also eliminating this base resistance from our small signal analysis, therefore eliminating that reduction in gain that we observed a moment ago. Same thing for this coupling capacitor. If we try to apply our input signal voltage without a coupling capacitor for our DC or large signal model, this would represent a path to ground, right? So effectively, we wouldn't, our emitter terminal would always be at ground for our DC operating point configuration, which in some instances isn't a good idea, and in other instances may be okay, right? Same thing for why we usually put a capacitor for our output as well. We definitely put one when we have a load resistance, because the load without a capacitor here at large signal would skew the DC operating point. So the capacitors are all about keeping the DC operating point constant while letting bits that need to go away to make our amplifier perform better happen. All right. Okay, see you guys later.